So one of the most important things to understand from this course is that e to the x, sine x, and cosine x have Maclaurin series, and they're very, very nice series. They converge everywhere. So the series actually do equal these functions for all real numbers x. So let's first of all develop them. I could actually use the formula to develop the series for e to the x, but I wanted to use the opportunity instead to show you something even more remarkable. So I've written out a series m of x equals the sum from n equals 0 to infinity of x to the n over n factorial, and I've expanded it for the first couple of terms, the first 6 terms up to degree 5. So what you want to do, I was going to show you this. Let's suppose that I take this series and I differentiate it. So I'm going to find m prime of x. So it's easiest to see if I just do it with the expanded terms. I could do it in theory with the terms that use with the general term, but instead I'm going to do it with the expanded terms. So the derivative of 1 is just 0. The derivative of x is 1. The derivative of x over 2 is, sorry, that's x squared over 2, it should be. The derivative of x squared over 2 is x. The derivative of I've written out here, by the way, 2, 6, 24, 120. These are n factorial. That's 2 factorial, 3 factorial, 4 factorial, 5 factorial. So let's find the derivative of x cubed over 6. That's going to be 3 times x squared over 6. And what we can see is that's going to be 3 over 6 x squared. So I'm going to write this as 1 half x squared. Go to the next term, the fourth term. So that's going to be 4 times x cubed over 24. 4 over 24 is 1/6. So this is going to be 1/6 x cubed. I'm going to write that. And finally the fifth, so that's going to be 5 times x to the fourth over 120. 5 over 120 is 1 over 24. That reduces to 1 over 24. So I can rewrite this as 1 over 24 x to the fourth. And we keep going. Now take a look at this series and the first couple of terms of this one. Notice that they are identical. So the derivative of this series is equal to itself. Kind of remarkable, isn't it? Well, think about this. What function do you know whose derivative is equal to itself? The answer, of course, is f of x equals e to the x. This series is in fact the series for e to the x. And in fact, we can verify because it's also the case that 100 e to the x is also its own derivative. So how do we know which one it is? Well, the thing about this is if we plug in 0 into this function, we get 100. If we're just talking about e to the x, we should get 1. If you look at the original series, m of x, if I plug in 0, I get 1 plus 0 plus 0 plus 0 plus 0, which is 1. So even though any function of the form c times e to the x is its own derivative, we know that it's this one because we know that it matches at at least one value. So anyway, so we can start out by writing that e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. This is a fact that all Calc 2 students should know. This is a very important series. The very important point of Calc 2 is that we can write e to the x in this form. Okay, so now I'm going to go on to sine x. Sine x we're going to do through the formula for Maclaurin series. Recall that the formula for Maclaurin series is the sum from n equals 0 to infinity of the nth derivative evaluated at 0 over n factorial x to the n. That's f of 0 plus f prime of 0 x plus f prime prime of 0 over 2 factorial x squared, and we keep going like that. So what I want to do is, you'll see the pattern if I do it up to degree 7. So what we're going to do is we're going to write out the function f of x equals sine x, and I'm going to write its derivatives up to the 7th derivative. So f prime of x is cosine x, f double prime of x is negative sine x, f triple prime of x is negative cosine x, f fourth of x, the derivative of negative cosine x is sine x. Look at that, we're back where we started. This just is going to go around in a pattern of 4. So this is going to be cosine x sixth derivative is negative sine x, and the seventh derivative is negative cosine x. All right, so since this is the Maclaurin series, what we're going to need to do is we're going to need to evaluate all of these derivatives at at 0. So I have f of 0 is equal to the sine of 0, which is 0. F prime of 0 is the cosine of 0, which is 1. F double prime of 0 is negative sine of 0, which is 0. F triple prime of 0 is negative cosine of 0, which is negative 1. The fourth derivative evaluated at 0 is going to be 0. This is just going to repeat. So I'll just write all these in. So I now have sine x and its first 7 derivatives evaluated at 0. And what we can see is that half of them are just zeros. Since the formula requires that we put in f prime, we put in the nth derivative evaluated at 0 and then multiply that by some power of x, half of these terms are just going to disappear. And you're going to see the interesting significance of that, by the way. So let's form the series. Let's write the series for sine x is going to be f of 0, which is 0. Then it's going to be f prime of 0. It's 1 times x, so I can just write x. F double prime of 0 over 2 factorial times x squared, but f double prime of 0 is 0, so there is not going to be an n equals 2 term. That's just going to be 0. Actually write in the 0 term so you can see this. So that's 0 plus 1 over 1 factorial x plus 0 over 2 factorial x squared plus, we're into the third derivative now, that's going to be negative 1 over 3 factorial x cubed. The fourth derivative is 0 over 4 factorial x to the fourth plus 1 over 5 factorial x to the fifth plus 0 over 6 factorial x to the sixth, and then plus negative 1 over 7 factorial x to the seventh. Let me remove all the terms that we don't need, all the zeros. So this is going to be x. Let's get rid of these 0 terms. I'll just cross them out. That's going to be x, so I've done that one, minus x cubed over 3 factorial. That's what that one comes out to. This one is going to be positive, so that's going to be plus x to the fifth over 5 factorial. And then negative 1 over 7 factorial, so that's going to be minus x to the seventh over 7 factorial. And we're going to keep going with plus and minus, dot, dot, dot. So look at what we have here. First of all, notice that we have only odd powers of x. It's x to the first, third, fifth, seventh, and it's going to keep going 9th, 11th, 13th, etc. And we also see that it alternates positive and negative. We have plus x minus an x cubed term plus an x fifth term minus an x seventh term, etc. This is significant because recall that sine is an odd function. Notice what happens when we write it as ascending powers, like it's almost a polynomial. Only the odd terms appear. What do you think happens with cosine, which is an even function? Think about that for a minute. So the formula for sine x is equal to the sum from n equals 0 to infinity of, the way I'm going to write this is, the first term is going to be, since we're starting with n equals 0, it's going to be, the first term is going to be positive, so I'm going to use negative 1 to the n. That's going to give me 1 for the sorry, actually that's wrong, because that's going to be the, yeah, no, this is the correct way to do this. So the 0th term, I know that doesn't correspond to a power of 0. You'll see in a minute how we deal with that. I'm going to put 2n plus 1 factorial x to the, I'm going to put the x up here actually, x to the 2n plus 1. So you'll see that if you keep plugging in ascending powers of x, you can try it out, but if I plug in ascending powers of x, it will generate these terms. This will be, this first one that you see, this will be n equals 0, This will be n equals 1, this will be n equals 2, this will be n equals 3. I know they don't match the exponents. That's okay. The exponents are generated by this formula, 2n plus 1. And you'll see that the factorials are also going to be generated by the same formula because we have x cubed over 3 factorial, x to the 5th over 5 factorial, x to the 7th over 7 factorial. So 2n plus 1 is generating the correct number to plug into both the exponent and the factorial. So let's put up here what the three series that you need to know. I'll leave cosine as an exercise for you if you want to try it. E to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, x to the 4th over 4 factorial plus dot dot dot. Sine x is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, x to the minus x to the 7th over 7 factorial plus minus dot dot dot. Cosine, maybe you can guess this, is going to be equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. That equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus minus dot dot dot. These are the three series that you should know. And by the way, if you look at cosine, as promised, it's an even function. It has only even powers of x, including this 1, which is like x to the 0. So that sort of explains the evenness and oddness of the functions sine x and cosine x. The last really neat thing I want you to notice about this is take a look at this. Sine x has only the even powers. Only the odd powers. Cosine x has only the even powers. E to the x has all of them. Yes, there are some extra minus signs in sine and cosine, but it starts to look like e to the x is kind of almost the sum of sine and cosine. Do you find that as freaky as I do? Well, it turns out that this is not a coincidence, and it turns out that they actually are related by an equation that we're going to see a little bit later. The way that we deal with these minus signs is going to be through imaginary numbers. It's going to turn out, and this is one of the most remarkable facts in all of mathematics, that once we allow for complex numbers, it turns out that e to the ix is equal to cosine x plus I sine x, where I is, of course, the square root of negative 1, imaginary 1. This we'll cover in a little bit of a later unit when we get to complex numbers at the very end of the course. But if it starts to look like e to the x, sine x, and cosine x are really almost the same functions as each other, they are. So, know these series. You should know what the series are for these three functions, and in a later video I'm going to show you how we use those.